Good morning, everyone, and welcome to the January edition of the Southeast Climate Monthly webinar, where we talk about climate and special topics pertaining to the Southeast region. I'm Sandra Rain, the regional climatologist from the Southeast Regional Climate Center, and I will be giving a climate overview. Our guest speakers today are Jeff Dober from the Southeast River Forecast Center, who will provide a water resources overview. Pam couldn't be here today, so Meredith Muth from NIDIS will be giving the agricultural impact update. And our special topic speaker is Vincent Brown from SCIP and Louisiana State University, who will talk about hourly precipitation trends in the Southeast. We thank them all for joining us. Just a reminder before we begin to type your questions in the question box at any time, and they will be answered at the end. Also, a recap email with a YouTube link to this recording will be sent out in the next day or two. Okay, let's talk about the climate. Temperatures over the past 30 days have been above average across much of the Southeast region, seeing about 3 to even 9 degrees above normal. December has been a particularly warm month. There have been 10 long-term stations that observed monthly mean temperatures that were ranked within their warmest December on record, including Montgomery, Alabama, and Pensacola, Florida. But as you can see from the image on the left, there were many more stations that ranked within their top 5 warmest Decembers on record. Several stations also saw a record number of days above 70 degrees Fahrenheit, including Raleigh, North Carolina, which had 12 days, and Florence, South Carolina, which had 17 days above 70 degrees in December. Precipitation over the past 30 days has been variable. December was relatively dry for Virginia and the Carolinas, but slightly wetter for parts of Alabama, Georgia, and Florida. However, the beginning of January saw a pattern change, and the precipitation has picked up across parts of Virginia and the Carolinas, whereas the Gulf Coast area hasn't seen as much precipitation. You'll also notice that the precipitation has been below normal for the mountains of North Carolina and Virginia. As a matter of fact, Mount Mitchell reported no snow for the entire month of December, and this was only the second time in its period of record going back to 1925 that this has happened. So far in January, however, it has already seen around 6 inches of snow. Moving on to the ENSO update, we're still under a La Niña advisory, with a 95% chance of La Niña continuing through the winter and a 60% chance of a transition to ENSO neutral during the spring from April through June. The next update, however, comes out this Thursday, January 13th. The U.S. Drought Monitor still shows some exceptional drought in the western part of the United States, but conditions are improving for many areas out west. Here in the Southeast, we've improved upon our drought conditions, especially in Virginia and the Carolinas. Puerto Rico and the Virgin Islands, however, has remained relatively consistent with their drought conditions, as moderate drought is seen across parts of Puerto Rico and severe and even extreme drought across parts of the Virgin Islands. And unfortunately, this drought is expected to persist. There is also the likelihood of drought developing for the Florida Panhandle. Hopefully, a relatively active pattern will keep it from expanding too much across the region. For the next 3 months, we have the probability of seeing above normal temperatures across the region, with the probability of drier conditions in the southern part of the region, and the probability of equal chances of wetter or drier conditions to the north. This is a very typical La Niña pattern. For the January 15th through 19th outlook, the 6 to 10 day outlook, there is a probability of below average temperatures for Virginia and the Carolinas, with equal chances of above or below for the rest of the region, and the probability of above average precipitation for much of the Southeast. Speaking of precipitation, it doesn't look like we'll see much through Friday. However, our best chance of precipitation comes Saturday through Monday, and for parts of Virginia and North Carolina, that might mean a little bit of snow. So to sum up, the Southeast has had above average temperatures for the past 30 days, and December was particularly warm across the region. Precipitation has been variable for the Southeast. We continue to be under a La Niña advisory, and the new update comes out this Thursday. Severe drought is in parts of the Carolinas, and Puerto Rico has some moderate drought. Our next system and best chance of precipitation comes around this weekend from Saturday through Monday, and the next 3 months will likely be warm and relatively dry. Now I'll turn it over to Jeff Dober with the Water Resources Update.
Okay, thank you, Sandra. So we'll start off here with our first slide, and we see here's the latest 28-day stream flow map provided by the U.S. Geological Survey. There on the left, and we see lots of green dots there in the map, meaning normal stream flows across most of the region. Many of those below normal levels that we were seeing across the Carolinas, the orange dots, for the most part, many of them have been alleviated by the recent rains and even the snow, which is a good thing during this primary recharge period. Looking to the right there, we see the, if you could go back, looking at the right there, the right map there, we see the latest regional stream flow conditions over time. And again, we see that last time we talked in mid-December, we were seeing this significant decline with the warmer temperatures and the drier weather that Sandra was talking about. But the jet stream got quite a bit more active into the deep south, and we had a couple of considerable precipitation events before and after the new year. And so you see that turnaround there in runoff stream flow levels well back into the normal range, which is a good thing during this time period where stream flows typically do increase. So pretty normal situation there. We'll go on to the next slide, and looking at it broken down by state, we see the same signal here in Alabama and Georgia, where we were trending into the below normal range back in early December at a time when stream flows should be increasing. We have made that turnaround, which is a good thing here in Alabama, Georgia, as well as a little bit in Florida. Florida and the Florida Peninsula is sort of slightly different than the interior southeast. But for the most part, what we're seeing is near normal stream flows across all three of those states. If we go to the next slide, this is even more so true across the Carolinas and Virginia, where we were heading into well below normal stream flows in some areas. The recent rains have helped pull us out of that impending stream flow drought, really, and now we're back in the normal range. So good news for those concerns we had back in early December for drought and water resource issues heading into the winter recharge period. It looks like the recent precipitation events have alleviated some of those fears for now, as this coincides with the map that Sandra was showing as well with the drought monitor. We go on to the next slide, but I also wanted to say we can't give up completely on this. Looking back at the analogs for La Nina for January, we see the red piece of the small pie charts there in the southeast. A lot of those pie charts, the red piece encompasses 50% or more in many locations, meaning during La Nina, stream flows tend to be below normal in most years. It's not 100%, though, as we do see, we have had some years with normal stream flow and even above normal stream flow, but this isn't as common for La Nina in January. And if we go on to the next slide, February as well, you can see that red shade there, and most of the pie charts there showing the red encompassing most of the probability. Again, the same thing here. La Nina tends to bring below normal stream flows. It's not 100%, but that axis of above normal across the Ohio Valley there, that's the green shade area, and the below normal, the red shaded area across the southeast. That shade can sometimes, that axis can sometimes fluctuate north and south. So we'll have to watch this going into the late winter and early spring. So we go on to the next slide here. Here's where we stand right now as far as flood conditions. This is the latest status map from the Southeast River Forecast Center, and we see several orange dots there, meaning minor flooding or nuisance flooding, river flooding ongoing across many of the coastal plain rivers of Georgia and the Carolinas. And this is from the rainfall we had back on the January 3rd, and even just some of the residual wetness that we had before the new year. Were somewhat wet in some of those headwaters, and so the rivers are flowing, and the yellow dots there those are the rivers at action stage levels, or what we call high water, where we have high water but no flood impact. So this is all pretty typical for this time of year. We generally have some rivers and flood during mid-January, and that's just the nature of the season. And we can see that going on the next slide. We see that here in the river flood climatology histogram for the Southeast. We're now in week 2 of the new year, and as you can see, river flooding typically increases in the number of events and magnitude as we go into early March. So like I said, river flooding is common for the Southeast this time of year. And really, if we didn't have river flooding, then we probably would be in a drought or dry conditions if we didn't have some river flooding going on this time of year. We'll go on to the next slide, and we also see evidence of this in our long-range forecast. This is our long-range ensemble streamflow prediction forecast probabilities posted on the long-range AHAP site. And basically what you see, there are a lot of orange dots, a lot of orange squares there, meaning that over the next 3 months, there's a greater than 50% probability of at least minor flooding at a number of these locations. Many of them in the coastal plain. The upper Tombigbee there, that's in the western part of Alabama and the northeast corner of Mississippi. That is a common location that we do see some minor flooding this time of year during the winter period, as well as down along the smaller coastal rivers in the Florida Panhandle and South Alabama, including the Suwannee River. Flooding during this time of year, minor flooding, fairly typical. Go on to the next slide. And so overall, what I would say for our January through March period is we're looking at maybe slightly below typical flooding. I think stream flows for the most part will be in that normal range to maybe edging into the below normal range, especially if we follow those La Niña trends as we get into February and March. So again, a more active jet stream there has brought several rain events here and improved our stream flow levels. But the question is, will this continue into February and March? And if we trend back to the typical La Nina, we will see some of those stream flows trending a bit lower, and maybe our chances for flooding to decrease slightly. So in summary, if we go to the next slide, again, recent events have resulted in improved conditions, which is good, and normal stream flows across most of the Southeast. Lake levels are near or slightly above their target pools across all the Southeast. I was looking at Duke Power, Alabama Power, and Southern Company, the core projects. They're all looking really good right now as far as being at their winter pools, or maybe slightly above as far as just water resources. But there is that chance with La Nina that we may have a trend toward drier weather, as the CPC outlooks have hinted. Drier weather, a return to drier weather as you go into the February and March period. But our river flood outlook mainly calls for slightly less extensive and less of a magnitude of river flooding than typical. But the good news, water resource issues becoming less of a concern heading into the peak recharge period. And we'll have to keep an eye on La Nina. So that's all I had, and I will pass it on to the next speaker. Pam.
Great, thank you so much, Jeff. Hi, everyone. Good morning. My name is Meredith Muth. I work with the National Integrated Drought Information System, NIDIS, as a regional coordinator. I am here on behalf of Pam Knox today, our usual presenter. We often include a few moments of agricultural impacts in this webinar series because the agricultural sector is often one of the first to respond to changes in climate, in particular to precipitation and temperature. So it's a good early warning sector to look at. I am going to not speak to everything on the slides. Please feel free to read it yourself, but just a quick reminder, as Jeff and Sandra have already articulated that this past month we've seen warm conditions across the region, and this has been both beneficial in terms of helping growth of forage and winter grazing, but has also caused some issues, specifically respiratory and livestock, fungal diseases, and extra weed growth. Looking at precipitation, the dry conditions have actually been extremely helpful for some farmers to feed hay. Dry conditions have led some farmers to feed hay, which has not been beneficial, but supplies are running low. There's some specifics here on different commodities, with including that citrus is starting to be irrigated due to dry conditions in Florida. Looking at chill hours, which are extremely important for many commodities, they are below normal for the season due to the warm December that was mentioned, but looking forward to coming cooler temperatures, which could help accelerate the accumulation of chill hours. And we will include links to the chill hours calculator that's shown here on the slide, as well as other resources in our webinar recap. Colder conditions are expected by mid to late January based on some long-range models, and this could bring frost to more of the southern area, Georgia, Alabama, and parts of northern Florida, and improve chill hour accumulation. Rainfall is expected to be below normal for the next couple of weeks, which again could increase some of the dry conditions, but there's a potential for heavier rain, in particular along the coastal plain. So that's something to look at the models, which of course will change as as time progresses. So quickly, in summary, dry weeks have allowed field work, planting, and harvest to catch up, which has been great for many. The warm conditions have a little bit of mixed blessing. Dry conditions have also started to decrease. We're starting to see drought withdrawal or lessen across much of the region, but we do want to keep an eye on the next 2 weeks, which could be fairly dry again. And in particular, as Jeff said, we want to keep an eye on the dry conditions because of the La Niña that's currently in effect. And then finally, frost has ended growing conditions in the northern areas. A cold outbreak later this month could freeze some areas that have not seen killing frost, but should probably not reach far into Florida. And so with that, it is a great pleasure for me to now transition to our special presentation for this month. We have Dr. Vincent Brown from SCIP, a RISA program, as well as Louisiana State University. And today, Vincent is going to talk to us about, sorry, we have the wrong title up here. He's from the Southern Climate Impacts Planning Program, which is a RISA program, but he is going to talk to us about precipitation trends, in particular, hourly precipitation trends in the Southeast. And so if you will hold on and give me a moment, I am going to transition to Vincent to provide him with the controls. So thank you for bearing with me. Vincent, you should have the controls.
Excellent. So can everybody see my title slide?
I can see it, yes. Thank you.
Excellent. Thank you so much. So today I'm going to talk about hourly precipitation trends across the United States. And again, my name is Vincent Brown. I serve as an assistant professor of research at Louisiana State University. I'm also the research director for the Southern Climate Impacts Planning Program, which again is a NOAA-funded regional integrated science and assessments team. And really, just to start, this work is from my dissertation. I'm going to talk about it and show you how it sort of led or created the foundation for some of the work that I'm continuing to do now for SCIP and for LSU. So briefly, let me move this little control panel down. This is what I'm going to, the structure of my talk today. I'm going to give you a little bit of a background as to why I decided to investigate hourly precipitation and hourly precipitation trends. I'm going to briefly go over some of the data and methods that we use in this project. That topic alone I could spend hours on, just because the dissertation, finalizing the data and the exact methods were quite arduous. I'm going to briefly go over some results and then provide you with some of the next steps that I'm doing and how this work has transitioned into something else. So first, why study hourly precipitation? What's so interesting about hourly rainfall? And it gets down to the fact that the way that we have observed precipitation historically is kind of limited. Most in situ data are recorded daily. For example, you get a one value summation of precipitation. It's either midnight to midnight value or 8 a.m. to 8 a.m. if you're a Cocoa Rods observer like me. But what that one value is, what that single value is a summation of precipitation characteristics. And when I say characteristics, I mean aspects like intensity, duration, or frequency. And these characteristics do not operate at the daily scale. As I mentioned, I'm a Cocoa Rods observer, and when I go out and measure my gauge, if there's rainfall in it, all I know is that, yes, it did rain, but I don't know anything about the intensity or the duration or the intermittency of that rain. So that one value kind of limits what I can deduce about that rainfall. And in fact, it rarely rains all day on days that it does rain. And to put this into perspective for you, in some years, some sites in Louisiana can receive roughly 50% of their total annual accumulation and roughly 0.56% of annual hours. So what does that mean? It means in some years, we can get nearly half of our rainfall in just 45 to 50 hours, which is kind of crazy. And I think a lot of you know this, most extreme or severe storms are associated with short periods of intense rainfall. So again, when we're just, daily rainfall is great, but when we reduce it down to one value, we're losing a lot of important information that can help tell us about the precipitation story. And again, just to kind of highlight what I'm talking about here, I like to speak about this event mainly because I was a victim of this event. I was walking across Baton Rouge's campus around 7:30, 7:45 in the morning, and the sky opened up. And I know that this image on the right is like a wet microburst, or what they call a rain bomb. This is not what exactly happened, but it's what my mental image of what happened was. So again, I was kind of walking across Louisiana's campus, LSU's campus, and the sky opened up and I got absolutely drenched. And when I got back to my office, I realized that we'd accumulated just over 4 inches of rain in 2 hours. And in being there, I can tell you most of it fell in about 45 minutes at the back half of 7 and 8 in the morning. And that volume of rain, just witnessing it in person, kind of blew my mind. And when I looked at NOAA's 14's average recurrence intervals, I found out that for Baton Rouge, roughly 4 inches of rain in 2 hours equates to a 1 in 25 year event. So it's a relatively rare event. You only expect, to experience that once every 25 years. When you zoom out to the daily level, if you accumulate that precipitation all across the day, and you look at the rarity of 4.9 inches, which accumulated over the course of that entire day, you have 4.9 inches, which happens in Baton Rouge once every year or two. So it's not very rare. So again, when you just use a single daily value, you lose a lot of very important information that can tell you a lot about the rainfall. So on top of that, so that was my first issue, sort of the first impetus for the work was trying to get more information on the precipitation story. And the second reason for doing this kind of work is obviously we have a changing or shifting climate. And we know that climate change is projected to alter or change the precipitation distribution. Kind of distilling it down to its most important point is that when the atmosphere warms, a warmer atmosphere can retain, or I know it's not the best term to use, but it can hold more moisture as explained by the Clausius-Clapeyron equation. And what that basically means is that as the air warms, the atmosphere can hold more moisture, and at a rate of roughly 7% per 1 degree Celsius increase in temperature. So what does that mean? Well, the water holding capacity of the atmosphere is a function of temperature. And help put that in perspective, 86 degree air can hold roughly 10 times as much water vapor than air that's 32 degrees. So obviously as temperatures rise, you can pack a lot more water vapor into that air. And why does that matter, especially for precipitation? Well, as we know, the climate is changing and shifting. We're retaining more energy in the system through the greenhouse effect. Not as much energy is escaping, so it's being trapped in the atmosphere. After a while, it ends up in the oceans, and it manifests itself as ocean heat content. Ocean heat content then raises sea surface temperatures, and sea surface temperatures, as they rise, it's easier for evaporation to occur. So what ends up happening is there's more water vapor or precipitable water that ends up in the atmosphere, and those tend to serve as a triggering mechanism for extreme events and these kind of short duration heavy rainfall events. And just to kind of finish up on the sort of impetus behind doing this work and how climate change kind of comes into play here is Trendburst 2011 put forth this idea of what could potentially happen with the hydrologic cycle going forward. And he used a good example. He used two stations, stations A, which is this top station, and station B on the bottom. These are gauges recording precipitation over the course of a month. Both station A and B record 75 millimeters of precipitation over that month, but the delivery mechanism of that rainfall is very different. Station A has a big gap or a long time between events, but when the events do occur, when that 75 millimeters occurs, it's very intense. And then station B, you can see the rainfall is more spread out, it's less intense, and it's more frequent. And his assertion is that potentially going forward, if we see enhanced or we see future climate change along the same trends that we're seeing, is that our rainfall distribution could shift and take the look more like station A compared to station B. And why is that worrisome? Well, we know that big rainfall events, here I'm highlighting the 2016 rainfall event, and then obviously Hurricane Harvey on the right. These are precipitable water diagrams, but we know that these extreme events, these heavy rainfall events, they require a lot of precipitable water. So if we continue to see high sea surface temperatures, high ocean heat content, which then leads to more evaporation, more water vapor in the air, we should expect more triggering or more moisture in the atmosphere, which can serve as a triggering mechanism for some of these heavy rainfall events. And again, I do a lot of work for a company called Applied Weather Associates, AWA. These are some figures from some of that work. But again, this is the August 2016 event where we estimated over 34 inches of rain fell in one location. And then again, Harvey here on the right. But the general takeaway here is that there's a similarity to some of these really, really big rainfall events. The moisture availability, the amount of precipitable water in the air fuels these big events. And two rapid attribution papers that came out and after these events, one specifically on the Baton Rouge event, said that what used to be an event with a return period of say 100 years should now be expected to occur on average once every 70 years or more frequently. And then a rapid attribution paper again after Harvey said, we concluded that global warming made this event 3 times more likely. And I always like to put an asterisk on this because Harvey was such a rare event that to say a super, super rare event was made 3 times more likely isn't, in my opinion, isn't really saying that much because again, that event was so rare that, 3 times a very, very small number or chance of occurrence isn't really that big of a difference. But anyway, to circle back to sort of the impetus of the work that I did, I like to say that our quantification of precipitation is limited, again, because most of the data occurs at the daily level. And then secondly, we have concerns regarding a changing climate. And I was interested in seeing how the changes at the daily level would manifest themselves at the hourly level. So that leads into the work that I did. And again, this was for my dissertation, and it's evolved and gone in 100 different ways, but today we're going to focus on some of the work I did in my dissertation. And the title of that was Climatology and Trends and Hourly Precipitation for the Southeast United States. So the goal was to first get a broad understanding of what precipitation characteristics look like across the Southeast United States. So our goal was to create an annual and seasonal climatology of hourly precipitation characteristics across the Southeast United States using data from 1960 to 2017. Here's our definition of the Southeast United States. And when I say characteristics, rainfall or hourly precipitation characteristics, I really mean 3 main variables. One, which is frequency. I often refer to that as precipitation hours. And that is to have a precipitation hour considered in our work, it was any hour with measurable rainfall. So it had to be greater than 1/100 of an inch that was considered a hour with rainfall or precipitation hour. And then duration, which I'll go over when we go over the time series stuff, and then intensity. To do this work, to investigate the climatology of hourly precipitation, we use data from 62 first order stations across the whole Southeast United States. These came from the Hourly Precipitation Database, HPD, one of the most reliable sources for hourly precipitation across in the United States. And then I'm going to spare you guys the gory details of how we quality controlled and created all the time series for each of these stations to get them up to par with some of the daily data. But once we created our annual and seasonal climatology, we then developed time series for each station, and we tested for trends in things like the number of hours that it's raining per season and per year. We tested for trends in the average duration of hourly events, trends for hourly intensity, and the frequency of 90th percentile events. Again, I'll go over what each of these mean here in a second. And for the temporal analysis for the time series testing, we narrowed down to 50 stations that had an overlapping starting time period. One big assumption before I show you a bunch of these climatology maps that we created of hourly precipitation characteristics is that our region, the region that we chose, is very big. If you spread out the stations that we had, the number of stations that we had, our representation is only one station per roughly 14,000 square miles. So to get around this, we had to use some interpolation techniques, kriging, again, to interpolate across this huge region. So the implication, again, is that we're estimating a lot over a very large area. So to see if this worked, the density of stations we had, we tested it for rainfall accumulation. So on your left here, we have PRISM annual. This is the annual accumulated precipitation for our region using PRISM. And then here's annual accumulated precipitation using the hourly stations for this work. And what you can see is the general pattern is pretty good. We have this nice gradient across Texas. You have higher accumulations across, the northern Gulf Coast. Then you have this little notch here across the Carolinas down into Georgia, which you can see all of that here in the PRISM data. But what you don't see is some of the features where we don't have stations. So again, for example, in the Ouachitas out in Arkansas and some of these higher values in western North Carolina and eastern Tennessee, that's not resolved because we don't have stations there. So you have to take this stuff with a grain of salt. That's why I put this here, because our interpolation is only as good as our station density. But the assumption here is that if it worked, if we were able to reproduce accumulations relatively well, that it would work for the precipitation characteristics, like the number of hours of rainfall, intensity, duration, and so on and so forth. So again, here is just PRISM, the climatology of PRISM during the summer, June, July, and August. And then here's our interpolated summer accumulation using our methods. And again, you can see the general pattern, again, mimicked it relatively well. So that gave us confidence that when we did this for the precipitation, hourly precipitation characteristics, it would generally show the same sort of overarching broad patterns. So here we go with those results. Top left, this is all at the annual level. We see the number of annual hours with rainfall, higher frequency of rainfall in the northern tier of the region in Tennessee and North Carolina, big gradient across Texas. Here again is the accumulation. So we have more hours with rainfall in the northern tier of the region, but more accumulation in the southern tier of the northern Gulf Coast. That tends to show you that the rainfall that occurs down here is more intense. We know that, and that's resolved here in the average hourly accumulation. The average duration of rainfall events tends to be longer, again, in the northern tier of the region, and this is all at the annual level. Breaking it down by season, here's winter. Same general pattern, more hours of rainfall in the winter in the northern tier of the region, but we accumulate more across inland of the northern Gulf Coast. Duration of events tends to be a little bit longer towards Tennessee and the Carolinas, but more intense events. The average amount that's accumulated hourly is higher along the Gulf Coast. Here we go for the spring. Same general pattern, higher number of hours of rainfall in the northern half, more accumulation in the central region. Here is our summer. Number of precipitation hours in summer shifts to the coast just like accumulations do. What's interesting is the average duration of the events. You see these little higher, this little pocket of higher duration events, and I think we concluded that was likely MCS, MCC activity occurring across Oklahoma. And then finally, fall, sort of the uglier plots of them all, but again, same general theme where we have higher number of hours of rainfall in the northern half of the region, a big gradient across Texas, and again, more intense events, higher average hourly accumulations across the southern tier of the region. So now we're going to talk about how we tested for trends. So for each one of those stations that we had across the region, we developed time series for them. And for each, for example, we created a time series with the number of hours that it rained, both seasonally and annually from 1960 to 2017. We did the same thing for accumulation. We then did this at the annual level for each station to derive hourly intensity. And what hourly intensity means in this study was we took the amount of rainfall that accumulated across the entire year and then divided it by the total number of hours that it rained in that year to get at sort of a rough metric of how intense that rainfall was. And then duration. So duration, to calculate that for each station, what we did was took the total number of hours that it rained at the station each year and then divided by the number of individual precipitation events that occurred at that station per year. And I'll get into what, I have one slide more specifically on duration to highlight it here in a second. And then the last thing we did was look at the frequency of 90th percentile hourly events. And what that means is for each station, we looked at its distribution of rainfall. So here's, for example, Baton Rouge's, and these are hourly accumulations. So we wanted to see at the hourly level, what is a heavy rainfall total at Baton Rouge? So any event that was the 90th percentile or greater for individual hourly events, we found the 90th percentile, and then in each year we counted the number of events that exceeded that threshold for each year for each station. And then a test for trends, we just did simple linear regression to see if there were any discernible trends. I know this is tough to see, these are small, but everything on the left side, so A, C, E, G, and I, are precipitation hours. And on the right side, B, B, F, H, and J here are accumulation trends. So I'll step you through each one here. A is the annual trend in precipitation hours for all the stations across the region. And what you can see is there's a little pocket here across Georgia, North Carolina, or South Carolina, Northern Florida, where the number of hours with rainfall between 1960 and 2017 were statistically significantly decreasing. And if you look at accumulations at the annual level, we did not see that sort of broad decrease in accumulation. So right off the top, we assumed that the rainfall in this little area must be becoming more intense because the hours that produce it are going down while accumulations were not changing that much. Diving right into winter, we saw the number of hours that it's raining during winter across sort of the eastern half of the region saw statistically significant decreases in the number of hours of rainfall during the winter. Again, with accumulations, that sort of broad decrease wasn't happening. So that again led us to believe that if the number of hours with rain is going down or precipitation is going down, but accumulations are not, there should be a slight increase in the intensity of winter precipitation. And then moving on to spring, again, a little pocket. It's interesting, everything seemed to be happening on the eastern, sort of in your guys' neck of the woods across the Carolinas and Georgia. But in the spring, a little pocket where we saw decreasing hours of rainfall during the spring. But that was accompanied with a decrease in accumulations, which was quite interesting. In the summer, we tended to see an increase in the number of hours of rainfall across Louisiana and Florida, but that was also accompanied with an increase in accumulation. And then fall, not much was going on. And then for the other three metrics, so A is our annual hourly intensity. So again, that was just the accumulation at the station divided by the number of hours that produced that accumulation. And what we saw was roughly half of the stations had a statistically significant increase in the average amount that was produced in those hours. So that is telling us there's a slight uptick in hourly intensity. And then B, which I'm going to dive into a little bit deeper here in a second, which is very interesting, is the trends in annual duration of rainfall events. And broadly across the entire region, 40 of the stations out of the 50 had statistically significant decreasing trends in annual average duration. And then finally, C, this was the frequency of 90th percentile hourly events. Again, we saw roughly just under half of the stations had an increase in the 90th percentile. So those heavy individual hour events from 1960 to 2016. But now I'm going to briefly dive into this sort of duration piece. So how we defined annual duration was we took, again, the number of precipitation hours at a station and then divided it by the number of individual precipitation events. So how we defined an event was consecutive hours with rainfall. So here's a good example to show you how we did it. If you had measurable rainfall in 2 hours and then a break, so no measurable precipitation was observed here, and then after that, 1, 2, 3, 4 hours of measurable precipitation and then breaks, what we would define this, our methodology would say this is 2 individual rainfall events, one of 2 hours, one of 4 hours. So your average duration here would be 3 hours. So that we applied that sort of logic to every single station and every single year, and then averaged all those values and tested to see if there's any trends in that. And what we saw again was this graphic down here, a large decrease in the average duration of events. And this is a sort of showing that for Charlotte here. So here you have 1960 to 2017, average duration, annual duration here on your y-axis. And what you see is a pretty significant decreasing trend in annual average duration. So what we were thinking is, and what we believe is happening is there's an increase in individual events, because if your denominator is increasing here, if there's more breakup of precipitation, more frequent events, as your denominator increases, it's going to drive down this total. So what our thought was, there's either more traces being observed, which were counted as 0 in our work, or more fragmented events or lower durations. So what we did was just a simple correlation to test to see for all these stations that the number of individual events was increasing through time, and 14 had statistically significant increasing number of precipitation events through time. So that's partly some of why we're seeing this large decrease in duration. And on top of that, there's a lot of stations that sort of have moderate trends. So we think it's sort of a combination of more increasing light events, or I'm sorry, more frequent precipitation events, and then on top of a sort of moderate or no change in precipitation hours that's driving this trend in duration that we see. So lastly, that was all my dissertation work. So this is kind of where we're going now, and a lot of the work that I'm doing now. I really did not like how we had to interpolate over such a large area. So a lot of the work that we're doing now, and I'm doing now, is using gridded precipitation products. However, there's a lot of caveats when you start using grids. I think everyone is aware that an 8-inch rainfall gauge is not equivalent to a 4x4 kilometer grid, which is also not equivalent to a quarter degree grid. So obviously we have gauges that are highly localized, and grids are averages over this whole grid box. So what we're trying to do now is testing different gridded products to determine which one sort of performs best with regards to precipitation characteristics. And when I say perform best, is closest to sort of what we observe at the gauge. So this product right here, or this graphic right here, is showing you month, January to December on your X, on your Y is number of precipitation hours. Black is, so this is just for Baton Rouge. This black line is the HPD, so this is what's observed at the gauge. And then this red line is just the raw stage 4 kilometer gridded product. And then obviously the little dotted lines are 95% confidence interval. But what you can see is that the number of precipitation hours using some of these gridded products is way, way higher, which makes sense compared to what we observe at the gauge, because you have this much larger area to where this can occur. But we're seeing these big discrepancies specifically in the summer months, which again makes sense due to these convective cells firing up, and it's highly localized event nature. Here's the same thing for precipitation days. So here's again number of precipitation days at Baton Rouge according to the gauge. Here's the number of precipitation days according to stage 4 in red. And this blue one is edited. We're just testing sort of some quality control, what we can do to get the HPD to look a little bit more like the gauge. But again, the bottom line is with a lot of these gridded products, the lighter events tend to dominate. So this is a frequency of very low accumulations. You can see the raw stage 4 products tend to have a lot more very, very low accumulation events. And that's what's kind of skewing the precipitation characteristics. And then lastly, here's just showing sort of the hourly precipitation distribution, again with the HPD in black, and then the original stage 4 in the red. Again, that should make sense, is you're averaging over a grid cell, you're washing out some of the bigger events, so your percentile events as they get bigger are going to tend to be lower in the gridded products compared to the observations. But sort of the key points, just to kind of summarize everything I just went through, was that using, and this is what I would say my key points were for this project at least, is that using daily precipitation totals does not tell the whole precipitation story. Obviously, daily data is crucial. We've been using it for so long. I mean, it's a vital resource. But again, it doesn't really tell you everything that you need to know about the precipitation. And again, even using, say we start looking at hourly precipitation, we're only using accumulations. That does not tell the whole precipitation story. We need to look at things like frequency, intermittency, intensity, and things like that. And this is where I think hourly data sort of helps supplement this. And then also beware of a potential bias in HPD. So if any of you are doing some analysis on event duration and you're using some of these stations in HPD, there is something going on with the duration component, potentially related to more trace events or more very, very light events, or just something is going on that's splitting the events up more, which is leading to, if you do analysis like we did, it looks like there are shorter duration events. And then finally, gridded products solve some of the issues, especially the spatial issues, but the temporal record, obviously with stage 4, it only starts in 2002, is not there yet. So with that, I will stop talking and I'll take any questions. Thank you so much.
Vincent, that was fantastic. Thank you so much for walking us through your dissertation. Just a quick reminder, if you have any questions or comments for any of the presenters or really anything about climate in the Southeast, we have a handful of experts online to help answer those questions. Go ahead and enter that now into the question box. I want to take a moment again to thank so much all of our presenters, Jeff, Sandra, and Vincent, and Pam. A recap email with a link to webinar recording and key takeaways will be sent out. It's easy for you to share with your networks or via social media, so feel free to do that. Our next webinars, again, this is a monthly webinar series. We will have flood climatology in the Southeast coming up in February. And in March, we're going to be talking about citizen science to understand weather and climate. Vincent mentioned the CocoRoss program, which is a really important citizen science-based program for us to have the important information to understand the trends that are going on across the region. So if you're interested in contributing to our understanding of weather and climate in the area, please tune in on March 8th. And following this, if you haven't taken our quick survey at the end, there's it'll help us improve this webinar series, or if you have any suggestions for topics you'd like to have, please let us know. So I have one question right now for Vincent. If, let's say if someone in the media saw your research and they asked you, are these trends related to climate change, what would you say?
So I've actually gotten that question a bunch of times, and it's always interesting to see how or what story the media wants to print. I can sometimes tell that they want to say something before they even ask to me. And when I distill it down and I say, yes, we are seeing more accumulations, which, and I'll say the buzzword, which is what they want to hear. I'll say, yes, and the intensity of hourly events is going up. They will take that and they will say, oh yeah, hourly intensity is going up. That's climate change related. But if you really distill what we did down and you look at some of the parameter estimates, the intensities are going up on the order of a few millimeters on average per year. That's a very, very sort of minor, unnoticeable, I mean, it's statistically significant, but it's not enough, in my opinion, that someone would notice it, just being an everyday citizen. So if, I always say that you have to take things with a grain of salt, and especially in this case, I think what we observed is consistent with a changing climate, but that doesn't mean that that is directly causing what we saw, if that makes sense. I'm always hesitant to go in and just because I don't know what's causing something, say that it's climate change.
It was a very good question. I mean, a very good answer. Thank you. It's a hard one to respond to.
Yeah, it's definitely tricky.
Yeah, it's a little tricky. It's anyways, here's one more question for you, Vincent. Do you have plans to incorporate recent or future events? And a recent example given was in Waverly, Tennessee, about 20 inches in about 12 hours. Do you have plans to incorporate these events to determine if they have statistical influence on long-term trends?
So I think that sort of work is being done by John Nielsen Gammon, the Texas state climatologist. He's done some really great work looking at how some of these more recent events, specifically, I think he was looking in Texas and Houston area, Harris County, looking at how some of these kind of recent events, these specifically heavy events, have influenced the trends that we've seen. So that's not really up my wheelhouse, but what I will say is that one of the things I do is I work alongside a company called Applied Weather Associates, and we kind of do a forensic analysis, and we recreate some of these really heavy rainfall events, specifically like the 2016 event, Harvey. We're planning to do a Melda relatively soon, and what we produce are depth, area, duration curves. So basically just telling you how much rain fell over a certain duration, over a certain area size. And we're always adding new storms to get a better sense of what's causing some of these big rainfall events. So I can't remember, I think you said something in Tennessee. What was the event?
The event was in Waverly, about 20 inches in 12 hours.
Wow, yeah, see, that's definitely something that we would love to analyze, just to take a look at sort of the meteorological, contributors that produce that event, and then again produce a DAD for that. So that's what we would do with it. Folks like John Nielsen Gammon, he's brilliant, his team is brilliant. They're the ones that kind of test how an event like that may swing sort of different trend metrics. I hope that helps.
Yeah, absolutely. Thank you. So I have one more last question before we wrap this up. This is what's really important aspect that you highlighted is how critical observation networks are to everything we do. So all of the early warning, whether it's for hurricanes, whether it's for floods, whether it's for drought, it all comes down to our ability to really monitor different types of conditions, precipitation being one of them. If you had, and you mentioned briefly a couple of areas where there was some gaps in the monitoring network and how you had to work around those. If you had one suggestion for, improving and sustaining our observation network for precipitation across the region, what would that be?
Well, I'm sorry?
Go ahead.
Oh, no, I was just going to say that I think there needs to be a lot more investment in sort of that infrastructure. I know some places, for example, Houston, after Hurricane Harvey, they had a really, really good, now I can't speak to its reliability, but I know that they had a really dense network of hourly rainfall gauges around Houston when that occurred. And we were able to, reconstruct and time the precipitation, really, really well because of that. So I'm not in politics or, city council or anything like that, but there, any sort of investment in hourly precipitation gauges, especially the ones, they're quite often at airports. They're expensive to maintain. They can be a little bit finicky and they have their own set of issues, but it doesn't have to be that. If we see there's a lot of technologies coming out now with automated gauges, tipping bucket gauges and things like that. If we can deploy those and, if the technology can get those out there and to where they're, don't need as much maintenance and we're confident in their reliability, that would go a really big way in, helping us paint a better picture of precipitation characteristics. And I think radar is doing that now. Like we have, our expanding radar coverages is helping us better understand, frequency of rainfall and things like that. But again, an investment in our networks would go a long way in helping us better understand precipitation and then helping put, some changes that we're seeing in the future in a better historical perspective.
Great. Another question just came in. How significant is the evolution of technology used to measure precipitation and calculated trends in precipitation intensity or duration? I can put it in the chat message so you can see the question.
Well, I think when I first started my dissertation, this was in 2016, 2017, sort of the gridded products were coming online, but at the hourly level, the resolution wasn't there. And now, I mean, most of the people that I work with now, and a lot of the people that are doing research in this area, a lot of them are using gridded products, and it's mind blowing to see just in how fast this is scaled and how fast people are learning how to use Python and R and all these languages, and they're using. I mean, it's mind blowing to see how fast we have adapted to these gridded products, and some of the stuff that we're cutting edge stuff. For example, there's a guy named Dr. Alex Haberly. He was at LSU and now he's at NIU. He's just, the stuff that he is doing is blowing my mind. And so with that rapid growth in the technology side of it, with these gridded products, it's great, but we also need to ensure that the products that we're using are grounded in sort of the observation-based stuff, the historical stuff that we've been measuring for 100 years. So the rapid increase in the pace is great, but I think we need to maybe slow down a little bit and get a better sense for how some of these products align with the observations and just get a better sense for that. And that's sort of some of the work that I'm trying to do.
Got it. And last question is, and maybe it's more of a statement, and I just put it in the chat as well, wondering if this type of analysis could be done on a state scale, or maybe it has been in an area where there's a high density of high quality mesonet stations, just to compare to the coarser regional scale. Has this been done?
Oh, yeah. Not that I'm aware of, but I would love to see that done. It would be great to, I think the biggest challenge is, and it's something that took me about a year, was quality controlling the hourly observations, making sure. And what we did is, and again, I didn't really go into detail on this because it takes a long time, but we compared all the hourly station data to the daily totals, because we had the utmost confidence in our daily totals. So that quality control process takes a while, and there's a lot of scripts to run and a lot of checking you have to do. But if you were able to do that in a really dense, sort of smaller area, and you could look at some of this stuff, that would be great. You would need sort of the climatological time period. You would need about 30 years to do it, but I think that would be great. I would love to see it done, and I would love to help somebody do that if they were interested to do it and they had the data.
Well, excellent. Okay, and with that, we're at the top of the hour. Thank you all for joining us for our first 2022 webinar. We hope to see you next month, and have a wonderful day.